Hey, good morning, everybody. This is Mr. Aynesworth here at Great Oak High School, Temecula, California, and we're in AP Pre-Calc this year in 2023, and we're going to go over a cool lesson about the rate of change over the rate of change. All right, so let's take a look at our goal up here. All right, so get your eyes up here. Given any polynomial function, so we have to talk about what a polynomial looks like in general, discover which rate of change of the rates of change is constant, okay? To do that, the best thing you ought to do is take a look at some first degree, second degree, and third degree functions, many examples, and look at the general trends and figure out what's going on, okay? That's the best way to learn because that's what was done in the very beginning, all right? So I'm talking about mathematicians. That's how they figure this stuff out, okay? They just don't look at one example. They look at many examples. So that's what we're going to do, all right? So the first thing we need to do is define a polynomial. So I'm going to say let n, which is going to be our exponent here in a minute, all right, equal the set of whole numbers. And if you don't know what whole numbers are, well, okay, they're the ones that you're familiar with when you're a kid. 0, 1, 2, 3, 4, etc., dot, 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 all the way to infinity and beyond, like Buzz Lightyear used to say. All right, and then a polynomial, we'll call it p of x, all right? You can go f of x, p of x, q of x, whatever. I'm just using p. That's just the name of our polynomial function. It looks like a sub n, which is called your lead coefficient, times x to the nth power. There we go, the nth degree polynomial. So the exponent, the highest exponent of a polynomial will let you know what the degree is, okay? In this case, it's n, all right? Plus a bunch of terms, dot, 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 plus a sub 2 times x to the second power. There's your second degree term. Your first degree term looks like a sub 1 times x to the first power. The exponent there is not needed to put up there, but I'm just emphasizing it here. Plus a sub 0 times x sub 0. All right, and typically people write this term right here just, this is equal just a sub 0, excuse me, because we know that x to the 0 power is equal to 1. All right, and that's called your 0 power rule. I'm not going to explain why that's the case. You're in pre-calc, you should know why. All right, so that's just a little side note right there, a little side note. All right, so most of the time you just end it with a sub 0 because x to the 0 power is 1. And a sub 0 times 1 is obviously just a sub 0. So you'll see that in all math textbooks, okay? All right, now let's take a look at case 1 here where n equals 1. We're talking about first degree linear functions. We're talking about lines. Okay, so what we want to do is explore the rate of change. When is it constant? So go back to the goal. Given any polynomial function, discover when the rate of change is constant. So we keep figuring out the rate of change of the rate of change until we figure out when it's constant. That's what we do. Okay, so here we go. I'm going to, so -1 minus -5, okay, which is called the difference there, gives us the change, all right? Or you can just think, from -5 on the number line to -1, you're moving right. How many units? You're moving 4, so you're going to add 4. So the rate of change is 4. The change from -1 to 3 is 4. Positive 4, that is, so I put plus 4. So always put a plus or minus because if it's increasing, it's going to be positive. If it's decreasing, it's going to be negative, okay? So the change, you got to represent that as a positive or a negative. So the change from 3 to 7 is a plus 4, and the change from 7 to 11 is a plus 4, and notice it's constant. Okay, so it's let's make a little note here. It is called a constant, all right, rate of change. And rate of change in my notes here is ROC, so constant rate of change. So again, remember, rate of change is ROC. And this has a special name here. Well, actually, I'll get to that in a minute. Well, it's called the first difference, okay? Now, why is that? Well, to get these changes, okay, you take the first or the second y value, okay, we'll call this y2, okay? And the first one we'll call it, well, we'll call that y1. And the way you get the 4 is you take the second y value minus the first y value. Actually, let me just put instead of algebraic, let me do the numbers here. -1 minus a -5. Guess what? That is 4. And the next one is 3 minus a -1, which is 4. So you take the second one minus the first one, or the previous one. So in general, you take the second y value and you minus the first y value. And that is why, instead of saying the constant rate of change, we call this the first difference because these are all found by differences, okay? You subtract, okay? So this 4 right here is called Yeah, it's a rate of change, but we're going to refer to it as the first difference. And in this case, it's always plus 4. So the first difference is constant. It's always 4 in this case. All right, so rate of change, another name for it, all right, when you do this right here, because you get it by subtraction, is called the first difference. Okay, so the same. So new terminology here today. We call the rate of change, when you do this the first time, it's called the first difference. If you do it another time, it's called the second difference. If you do it another time, it's called the third difference, and so on. All right, so let's see if this is always the case for all linear functions. So I got 2 more. All right, so this has to happen over equal intervals, by the way. So let's see over on the left if the intervals are equal. So from -2 to 0 is a +2. And then we have 0 to 2 is +2. And then 2 to 4, +2. So it looks like we have equal intervals. And this is important. So I'm going to make a note of that in red. Okay, so equal intervals. So equal intervals, all length 2 in this case. All right. So the first difference is constant over equal intervals. All right. All right, so now let's apply it on the second one. So first of all, on the second table here, our interval, it looks like it's 3, okay? Okay, so +3 again, +3 again, +3 again. So we have equal intervals on the left. What's going on the right? So let's take a look at the first difference, or called the rate of change, or the first difference man. Okay, so -2 to 0 is a +2, 0 to 2, +2, 2 to 4, +2. So this one's really easy to see. So notice here that we have a constant first difference. So constant, what's called a first difference, and that implies that we have a linear function, okay? Okay, first degree, so first degree, first of all, okay, and we call those linear functions. All right, now remember, the first difference is called a rate of change, and you guys know for all linear functions, the rate of change is constant, because we have a line as opposed to a curve, okay? So you got to put all these ideas together in your head, okay? The reason why we have a rate of change of 2 and that's constant is because a line always has a constant rate of change and a constant average rate of change, which is called the slope of the line, okay? All right, so how about this next one here? So over here on the left, from -4 to 2, that's a +2. Again, I'm looking for equal intervals right here. So from -2 to 0 is a +2. So it looks like we have equal intervals on the left. Very good. Now on the right, what's going on? So let's take a look here. So from -21 to -13, we're moving right on the number line. So we're getting bigger. So it's increasing. Okay, because the slope's 4, it's increasing. So we have a +8 from -13 to -5, +8 again from -5 to 3, +8. So -5 plus 8 is 3. 3 plus 8 is 11. So we'll keep adding 8 here. And again, we have a constant first difference. So constant first difference, what does that imply? It implies that we have a first degree linear function. Okay, so it's a constant first difference, constant rate of change. In fact, let me write that again, just so you guys understand the flow and the logic here. So the constant first difference means that we have a constant rate of change, okay? That implies that we have a linear function. Okay, there we go. And so let's generalize it here. So get out your red pen and let's write it in generalization here. Or what do we observe over 3 examples? And again, this is not a formal proof because these are only 3 examples out of infinite many, but you know, it gives a kind of idea that we're gonna assume here that for any linear function, let me spell that right, okay? So for any linear function, and it's first degree here, okay? First degree function, for any linear first degree function, all right, the first difference is always constant. So the first difference, which is called the rate of change, okay, is always constant. Put a big bold letters, okay? There we go. Now, what happens with quadratic functions, which are second degree, and what happens with cubics. So the way you figure that out is you go for it, all right? And you do the same thing, and you analyze it the same way, and then you figure out what you need to know. All right, so this has to happen over equal intervals. So let's analyze on the left first. So -4 to 2 is a +2. -2 to 0 is a +2. So it looks like we have equal intervals on the left. Let's go for it on the right. So from 16 to 4 is a decrease of 12. From 4 to 0 is a decrease of 4. Or you can take 0 minus 4 is -4. 4 minus 0 is 4, so it's increasing now. And then from 4 to 16 is an increase of 12. Well, this is not constant, first of all. Okay, so right here, okay, the first difference is not constant. First diff, all right, that means it's not constant. That means it's not linear. I'm writing down my thought process here. So my thinking, okay, so when I see a first difference and it's not constant, that tells me right away it's not linear, it's got to be something else. Okay, now I give you the x squared function, so you know it's quadratic. However, typically you're not given the function, you're just given a table of values, and so you really don't know. So what you have to do, so let's switch colors here. You got to take a look at what's called the second difference. And the second difference here from -12 to -4, you're increasing here, so you have to add 8. -12 plus 8 is -4. -4 plus 8 is 4, so the change is 8. And again, from 4 to 12 is a change of 8. So notice that the second difference here, this is called the second difference now, because we did it twice, right? So it's called the second difference, all right, and it is constant. Now this implies that we have a degree 2 function, which is a quadratic, okay? Quadratic, second degree. So you got to hook that into your mind. When the second difference is constant, you have a quadratic function and not a linear function. Now, is that true for all quadratics? Well, we can't really prove it, but we can do it 2 more times to see what the general idea is. Okay, and then, so this has to happen over equal intervals. So we have to check the intervals on the left to make sure they're equal, and then we figure out the rates changed on the right. All right, so on the first one here, the second difference is constant over equal intervals. And then the second one, well, let's figure it out. So from 48 to 16 is a decrease of, looks like 32. Okay, so it's decreasing here. So 16 minus 48 is 32. 0 minus 16 is -16 because we're going down. There's no change here. And now we're increasing, so plus 16. And here we're increasing 32 because 16 and 32 is 48. Now, so once again, first difference is not constant, it's not linear, so then you do it again. All right, so what's the rate of change of the rate of change? So what's the change from -32 to 16? We're increasing again because we're moving to the right on the number line, and so this is a plus 16. From -16 to 0 is plus 16. From 0 to 16 is 16. From 16 to 32 is 16. So again, right here, the second difference, all right, is constant. So you make a note of that. All right, and that implies that you have and over equal intervals too, by the way. So on the left, the interval is 2. So plus 2 here. Notice that we're dealing with equal intervals of x here. And when the second difference is constant over equal intervals, you have a quadratic function. Okay, there we go. Now let's take a look at one more quadratic. And notice the quadratics up here, I've given them to you. So the first one is x squared, the next one is 2x squared minus 4x, and now the third one here is x squared minus 2x plus 1. So I'm starting off with quadratic functions just to show you the nature of them, you know, the qualities of them. And here on the left, we have equal intervals of 1. Okay, so this is just length 1 on the left. All right, from -1 to 0 is plus 1. So we have equal intervals on the left. On the right, what's going on? So from 25 to 16 is a decrease of 9. So this is going to be a -9. From 16 to 9 is a decrease of 7. From 9 to 4, it's a -5. 4 to 1 is a -3. From 1 to 0 is a -1. And these are not constant, so it's not linear. So it's got to be something else. And so you keep on doing this until you get a constant, or a rate of change, that is. So from negative 9 to negative 7 is an increase of 2. From negative 7 to negative 5 is an increase of 2. From negative 5 to negative 3 is an increase of 2. And from negative 3 to negative 1 is an increase of 2. So because the rate of change is constant over equal intervals, okay, which we call the second difference to make it simple. So the second difference, which is the rate of change over equal intervals, is constant. So the second difference is constant over equal intervals. That tells me that you have a quadratic function, okay, which is a second degree function. Now let's generalize it. So for any quadratic, okay, which is a second degree now, all right, the second difference is always constant. Now this is not a formal proof, but it happens to be true. So you can assume that. So when you don't know what type of function you're dealing with, and you take a look at the rate of change of the rate of change, whenever it's constant or whenever it becomes constant, then you know the degree of the function is basically what you're learning here. Now in case 3, the third degree function here, I gave you a bunch of third degree functions. So let's do the same sort of thing. Notice all the cubics are different. Okay. So let's analyze and see what's going on. All right, so from negative 7 to 2 is an increase of 9. All right, because you're going right on the number line. And this happens over equal intervals. So this one's plus 1. Looks like the interval length is 1 here. Looks like it's always 1. So we have equal intervals on the left. So we have equal intervals on the left. Cool. On the right, we have a decrease from 2 to 1 is obviously a decrease of 1. From 1 to 2, it's an increase of 1. From 2 to 17, it's an increase of 15. And from 17 to 58, what is that? Well, it looks like if you add 41, okay? Now, these are not constant rates of change, so it's not linear. Okay, so this tells me here, first difference, okay, not constant. So not constant. Okay, not linear. That's the first thing I'm learning here. Let's take a look at the second difference. Okay, so from 9 to negative 1, we're moving left on the number line. Okay, so that's a minus 10. From negative 1 to 1, look at this. This is weird. That's an increase of 2. And then we have an increase of 14. And then we have an increase of, looks like 26. Okay. Now, so the second difference is not constant, so it's not quadratic. So this tells me the second difference, okay, is not constant. That tells me that it's not quadratic. Okay, so now we keep on going. So you keep on going until you get a constant difference. So let's see what we have here. So from negative 10 to 2, that's an increase of 12. From 2 to 14 is an increase of 12, and from 14 to 26 is an increase of 12. So this is a constant third difference. So constant third difference. Okay, so what that is, it is a rate of change of the rate of change of the rate of change. But saying that all the time is difficult and it's somewhat confusing at times. So the easiest way to say that is it is a third difference, and if it's constant, that tells you have a cubic function, which means you have a third degree function. Now, is that true for all cubics? Well, let's try 2 more and see what happens, okay, to get an idea. So on the left are equal intervals, okay? I'm looking at the second table now. And again, from negative 2 to negative 1 is a plus 1, and obviously from 0 to 1 is 1, 1 to 2 is 1, 2 to 3 is 1. So we have equal intervals on the left. On the right, what's going on? So from 25 to 6 is a minus 19 because we're decreasing here. From 6 to 1 is a minus 5. From 1 to 2, negative 2 is a minus 3. And from negative 2 to negative 15 is it's more negative, so minus 13. And then here from negative 15 to negative 50 is minus 35. So it's not linear because the first difference is not constant. And now we do it again. So from negative 19 to negative 5, now we're moving right on the number line, so we're getting bigger, so we're increasing by 14. From -5 to -3, that's an increase of 2. Now we're getting smaller. So now -3 to -13 is a decrease of 10, so it's a -10. And then here we have -13, -35. We're moving left on the number line, so we're decreasing by 22. And when I say decrease, that's a minus, right? So these aren't constant, so guess what? It's not quadratic, okay? So now keep on going. So from 14 to 2 is a decrease of 12, so a -12. From 2 to -10 is a -12, and from -10 to -22 is a -12. So now we have the third difference is constant. So this tells me that we have a constant third difference, and that tells me, I'm going to write my thoughts, that we have a cubic function, which is a third degree function. So this is cubic. All right, and that always happens with cubic, by the way. That's why we're doing this exercise here, just to see it, because it's not enough just to see it for one example. You need to see it for multiple examples to get the idea. All right, and this happens over equal intervals, by the way, because I'm giving you equal intervals on the left, even on the third one here. So let's try the third one. All right, from 17 to 5 is a decrease of 12. 5 to 1 is a decrease of 4. From 1 to -1 is a decrease of 2. And then from -1 to -7 is a decrease of 6. From -7 to -23 is a decrease of 16. So it's not linear. Okay, so we do it again. So here, from -12 to -4 is an increase. Now we're moving right on the number line, so it's an increase. From -4 to -2 is an increase of 2. Now we're decreasing. -2 to -6 is a decrease of 4. And then from -6 to -16 is a decrease of 10. So make sure you put the plus or minus, because the numbers are either increasing or decreasing here. And then, okay, so these aren't constant, so it's not quadratic. So, well, guess what? You do it again. So from 8 to 2, we're decreasing by 6. From 2 to -4, we're decreasing by 6. From -4 to -10, we're decreasing by 6. And so this right here, this number represents a constant third difference. Or you can say the third difference is constant. We'll say it that way. It doesn't matter how you say it. So, third. Come on, Aynesworth. So third difference, because we did this 3 times, right, is constant. All right, that tells me we have a cubic function. Okay? And so let's generalize it. Okay, so for any cubic, which happens to be a third degree function, that tells me that the third difference, okay, is always constant. All right. Now let's generalize it for the nth degree. All right, so let's put this in red here too. All right, so here's the general conclusion. Okay, what you need to know and you need to take with you for all your activities. Okay, so for any nth degree polynomial, nth degree, all right, polynomial, all right. All right, so what does that look like? Well, it looks like P of x is equal to a sub n times x to the n plus plus a sub 1 times x plus a sub 0. Okay, so there's your polynomial in general, nth degree. So notice the exponent is n there. All right, the nth difference, okay, the nth difference, all right, is always constant, always. That's a big word too, okay? So if I say sometimes, that's one thing. I said always, is always constant. So if n is 1, you have a first degree linear function like at the top, all right? The first difference is constant. When n is 2 and you have a quadratic, which is a second degree function, the second difference is constant. When n is 3, you have a cubic function, the third difference is constant. If you have n equals 4, God help you, all right, you have a fourth degree polynomial, the fourth difference would be constant. And it goes on and on and on. And that is the main idea, all right? All right, so that's it. So now all we have to do is apply it in class and to other things. So this is Aynesworth here. If you need more help, more assistance, just see me in school, all right? And I will see you in my next lesson. All right, bye-bye.